Hello, in this video we are talking about waves. What even is a wave? That's what we're going to get into. This is the introduction to topic C2 called wave model. So often when we're talking about waves, the probably main thing you think of when you think of a wave is you're thinking of a traveling wave. The deal with a traveling wave is what is traveling? Well, the thing that's traveling, believe it or not, is energy. So a wave is a thing that moves energy through space. A big key idea that's an important one that the IB likes to ask you about is that a wave transports energy and not matter. So it's not stuff moving from point A to point B in a wave. The thing that's really moving is energy. And a wave almost always needs a medium, something to travel through. So picture a wave in the ocean. The medium is the water in the ocean. And the wave is some sort of abstract and vague idea, but it's some energy moving through that water. Sometimes you'll see something called a wave pulse. So take a slinky like so and just vibrate it back and forth once. That's really a wave pulse. A wave is a more continuous, constant thing. But either way, you're doing the same thing, which is carrying energy from point A to point B. Imagine if this hand here, this person was moving this slinky up and down constantly back and forth. You would then have what we would officially call a wave, which is this, constant, caused by this constant continuous disturbance or oscillation. Oscillation meaning a back and forth movement like so. So there you go. Energy's moving. Notice the slinky itself is not, moving left to right in this picture, even though clearly something is. The something that's moving is energy. In this case, notice the slinky pieces are moving up and down. Oh. Okay, so that's a type of wave called a transverse wave. It's probably the main picture you have in your head if you're picturing a wave. So a transverse wave is defined by that whole direction thing. In a transverse wave, the particles of the medium, the particles that make up the wave, the coils of the slinky, if you will, are moving perpendicular to the direction of travel of the wave. Perpendicular is the key word. Here's a fun little animation of a transverse wave doing its thing. I think if you just look at this like big picture, kind of let your eyes blur and relax a little bit, there's something moving left to right. Like focus on kind of the peaks maybe, and I think we can see there's definitely some motion left to right of perhaps energy, it seems like is what we're saying. But now focus on any one of these like little, dots. These are the particles. I think each one individually is just moving up and down. So that defines a transverse wave. The particles are moving up and down. The wave itself is traveling like horizontally left to right, so they're perpendicular. A wave on a string / slinky is a good classic example of a transverse wave. A stadium wave, if you do the wave at a football game or something, that's a transverse wave, right? These dots could all be people standing up and sitting down, making an exciting wave through the stadium. Also an electromagnetic wave, an EM wave, is a big example of a transverse wave that we will talk about a whole lot because that is light, is what that is, an electromagnetic wave. And we'll spend many lessons and units and have a lot of fun studying light and the specifics of the electromagnetic wave, but it is a transverse wave. For transverse wave, we'll often name the peaks and valleys, the tops and bottoms of the wave are crests and troughs, is what we're going to call those. So point up at the top, we call a crest. Point down at the bottom, we call a trough. Another type of traveling wave, there is another way you can wave energy through space, and it's with what we call a longitudinal wave. And this is sort of opposite of a transverse wave, whereas here the key word is parallel, where before it was perpendicular. This one's a little weirder, conceptually maybe, but it's the same general idea. You have particles vibrating, and by being sort of connected to each other or bumping into each other, in this case, you're transferring energy from one end to the other. So here these particles are definitely moving horizontally, and so is the wave. I think we can definitely see a sort of compression wave, we sometimes call these, going left to right. But this one especially is sort of an optical illusion, like you're probably right now picturing, hey, look at all those particles moving all the way from this side all the way to this side. They're not. Watch any one. This one's fun. They have a couple like highlighted in red. So watch any of those red particles. Oh, ooh. They just go side to side, right? And they don't go very far. They oscillate back and forth horizontally. Pick any point, even one of these points here. Oh, well, look at that. All of the particles are really moving left to right, and you get this total overall effect of this energy transferring down, these kind of points where at any moment in time particles are close together, points where they're spread out. But no particle is moving very far left to right. Right? Watch them all. They're just going side to side. So a sound wave is the main example of a longitudinal wave. You are hearing me right now through a longitudinal wave. Air molecules are bumping into each other, and they're transferring energy in the direction that they're kind of vibrating as they bump. You can also make a longitudinal wave on a slinky if you want. Take the slinky and like push it forward and backwards rather than like side to side or up and down. And you'll get this fun looking thing where there's points where the slinky coils are really close together and points where they're far apart. Just like here, points where particles are close together and far apart. Instead of peaks and troughs, because they're not, it's not like a peak of a hill anymore, we call those compressions and rarefactions. Fun. So they're sort of like the analogy to peaks and troughs, or crests and troughs. It's like the same general idea. But in this case, since everything is along one axis, it just looks a little weirder. So we call these points compressions and we call these points rarefactions, which again are like the crests and troughs of a longitudinal wave. So some properties of a wave that you want to know about, some of these different things we're going to describe. We got crests and troughs here. Let's do two more. Let's talk about wavelength and amplitude. Okay, wavelength. The word length is in the name. That should be your clue that this is going to be a measurement like of some kind of, distance or length. We're going to measure it in meters, for example. So it's a physical distance. It's a distance between 2 points. Think of it as the kind of crest-to-crest distance, peak-to-peak distance. That's probably the easiest way to think of it. Officially, it's the distance between 2 points in phase, 2 consecutive in-phase points. Meaning 2 points that are doing the same waving thing at the same time. So 2 peaks are a good example of this that are easy to find and kind of measure the distance between them. But I could pick like this point over here on the left side of this bump and this point, same point over here on the same left side of this bump. And the distance between those 2 points would be a wavelength. Or the distance between like this 0 and this 0 would be a wavelength. Or between the trough and the trough would be a wavelength. Okay, so it's the length of the wave, truly, in meters, side to side. Amplitude is measured sort of the other way, depending on the type of wave. If you got a longitudinal wave, it's more fun. But amplitude is defined as maximum displacement from equilibrium. So for a transverse wave, at least like this, think of it as the height of the peaks. It's the maximum displacement. So amplitude is like a fixed value typically for a wave because it's just the maximum, whereas the displacement of the particles changes constantly over time. The amplitude is just the maximum displacement you get. Math enthusiasts probably know a little bit about amplitude. It's like the number out in front before you multiply by sine of blah, 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 something like that, if that helps at all for you math people. But it's the height of the wave is really what the amplitude is. One other fun one, and math people, sorry, this is where it will get maybe a little confusing because we use these words differently in math and physics. In math, when you're talking pure math, stuff's on Y, stuff's on X. You're just doing it for the pure joy of doing the math. In physics, though, we got to give these things some physical meaning, and so we care what thing is on X and what thing we're looking at. Anyway, when we talk about period is a measurement of time. So period is a measurement of time. Officially, we call it time period. We'll almost always just say period. We're going to use capital T for this, and it's the time it takes for one cycle of the wave, essentially. Really, the time it takes for one particle in the medium to do one full cycle. So think of it as like the time for one cycle of the wave. So it's a measurement of time. The opposite, reciprocal of period is called frequency. And frequency, if period is how long it takes for one cycle, Frequency is how many cycles happen in 1 second. So frequency is measured in what we call hertz. A hertz is a cycle per second. Cycle is sort of a ghost unit. It's like a dimensionless, doesn't really count kind of unit. So math-wise, this is just a per second. Kind of means a cycle per second is what 1 hertz is. So they're reciprocals of each other then. Here's a data booklet equation, a nice simple one that tells us this, that the period is equal to 1 over the frequency. So picture you have, a rubber ducky in your bathtub and you're bouncing it up and down. Let's say you bounce it up and down 5 times per second. Well, then you're talking about a frequency of 5 hertz. And that means the period would be 1 over 5, a fifth of a second would be the time for 1 cycle. That's the idea. If this helps, you can think of frequency as cycles per second and period as seconds per cycle. That's kind of the idea of these two things being reciprocals. So we can put all that together to find an equation and talk about the speed of a wave. Wave speed, the speed of a wave is constant, is typically constant as long as nothing with the medium is changing, because wave speed, it seems like, depends on the medium. So like a sound wave will travel at the same speed through the air, unless you change something about the medium, like the temperature of the air. Wave traveling through a slinky or a string. So make a wave on a slinky. You cannot change how fast that wave goes unless you change the tension of the slinky. The amplitude, for example, will not affect the speed of the wave, amazingly. Even the frequency that you create the wave at will not affect the speed of the wave. So wave speed is kind of a set thing, but we can measure it based on how far a wave goes in a certain amount of time, which we would do like this. So since the speed is constant, in a given medium, we can do this. Just distance over time is all we're doing here to find the speed of a wave. So we're going to use V, just the generic V, for wave speed, and it's equal to wavelength over period. 3-part equation, because we can also do this fun frequency thing. But this is a good one to focus on because we really are just doing distance over time for speed. Since it's a constant speed, we can get away with that. Divide the distance in meters by the time in seconds for 1 full cycle. Because the distance traveled by the crest of a wave, if you want, in 1 cycle is the wavelength, and the time it takes for that cycle is a period. So distance over time will give us that average speed, the constant speed of the wave, this sort of abstract idea of some energy moving through. And because period equals 1 over frequency, we can do some mass substitution, and that means it would be the same thing as frequency times wavelength. You probably see this one a little more often, but it kind of comes from this basic idea of just distance over time. Okay, this means because V is typically a constant, again, the speed of a wave on a slinky is not going to change if you change F. This is set. You can change it by changing the medium, but it is what it is. So that means these two things are inversely related if I talk about wavelength and what it relates to. Well, if V is set, then increasing F will decrease wavelength and other way around, since that's how math works with fractions, right? If I double the frequency that I'm waving my slinky at, I'm thinking the wavelength would cut in half. That would be what this inversely proportional means. Here's a little animation that kind of shows that idea. So here we have 2 waves, a blue one and a red one. They are definitely both moving at the same speed side to side. I think we can just kind of see that here, that they're traveling at the same rate side to side. The red one has double the wavelength of the blue one. And what that means is it's got half the frequency. Frequency you could think of as, you could figure it out by counting how many peaks pass a certain point per second. So you could kind of talk about the, rate at which the peaks pass over here. So you got a peak, and then peak, and then now, and then now, right? So that's the frequency is how many peaks per second if you want. Down here, they're closer together, so you got a much faster now, and now, and now, and now. You got a much faster frequency for the blue wave. And we just picture what's happening. Physically that should make sense. If they're going at the same speed, and then the blue one, the peaks are closer together, well, then those peaks are going to pass you at a faster rate. That's all we mean by wavelength and frequency, and why they kind of have this relationship. Okay, and when we deal with waves, we're often looking at graphs. Wave graphs can be confusing because it super matters what's on each axis, and there's two main types you're going to see. This is an easy thing to get confused about. Okay, when you see a picture of a graph of something happening with a wave, y should represent the displacement of the particles in the medium. So y is showing you how far particles are above or below their sort of rest position, the equilibrium position. So that's y. Y is going to be displacement. There's two different things you can put on x, though. One of them is distance. This is so fun. You can make a displacement versus distance graph. Something in meters on x, something in meters on y, but totally different things. All right, so think of this as a picture of the wave. This graph has nothing to do with time. So what we're really looking at is we're looking at one moment in time. We're looking at all the particles on a wave at the different locations along the wave. So x-axis is the physical distance along the wave. Distance is maybe not even the greatest word for this, because to me, distance implies like a start and an end. That's not what's happening here. Distance is just where you are on the x-axis. Okay, so this is plotting what the displacement of every particle on the wave is at all the different positions along the wave, like horizontally. Meaning you could directly measure wavelength from this graph. This wavelength is just the distance between 2 points. You would just measure on the x-axis how far from one peak to another, and that's your wavelength. Be careful, though, because you can't find period. So again, this is a math class. This stuff means stuff. You can't find period on this graph because this graph has nothing to do with time, and period is a measurement of time. So this graph will only give you a wavelength. You can get a period, though, if you have this graph, displacement versus time graph. This graph will look exactly the same as a displacement versus distance graph in its shape. They all look like sine waves and cosine waves and stuff. So you got to really think about what's on each axis and give meaning to it before you do any thinking and interpreting. So if it's a displacement versus time graph, what we're talking about is one particle. And we're tracking one particle over time where it is vertically. If we're talking a transverse wave, we're talking about its displacement over time. When you graph the displacement over time, you get the same like wave shape, but what we're looking at is just where this particle is as time goes on. So in this case, the x-axis represents time, meaning you could find the period from this graph by measuring, again, the peak-to-peak sort of distance on x. Just that distance now is an amount of time, because time is what we're measuring on x. Yeah, so that would give you the time it takes for that one particle to get back to the same point in its cycle, which is what we defined a period as. So be really careful with these two graphs. They can definitely get confusing with all graphs, especially these graphs, but truly all graphs in physics. Always pause. Don't assume that it's a picture or that you know what you're looking at. Read what's on Y, read what's on X, think about what it means, and then start interpreting. Okay, so last, here's just one example of a displacement versus distance graph, because this is the weird one. It really is like a picture of the wave. So up here is like, this is the idea of a sketch of the actual physical wave we're representing. So maybe this is like, a wave in water, and we have like little beads floating on the water. So displacement versus distance means I would look at every single particle in the medium, and I would plot the displacement of each particle at every distance along the wave. So when I'm like, 2 centimeters along the wave, that would be my distance. So it's really, positioned this way. When I'm at 2 centimeters distance-wise, the displacement is 0 because this red particle is at its equilibrium position. When I'm like 5 meters along the wave, though, so when my distance is 5 meters or 5 centimeters on this picture, the displacement is where this blue particle is, which is some negative value below equilibrium. So this is your displacement up and down. Your distance is like where you are side to side. So again, we're plotting the displacement of the particles at all these different distances along the wave. It really is like a picture of the wave. Okay, so there you go. There's some intro to waves ideas for you to noodle on. We will have lots of waves fun to come. See ya.